And welcome back, ladies and gentlemen, to the Simpkins Physics Corner. Two examples for you. One is a horizontal projectile, one is an angled projectile. So let's get into a little sample here. So after losing a round of Call of Duty, Francis throws his Xbox One out the window horizontally. He throws it from the third story of his dorm room, which is 8 meters off the ground, and it goes out with a horizontal velocity of 10 meters per second. How far does it land from the dorm building? So when it says how far does it land from the dorm building, we're talking about x, the horizontal distance, and y is how high, so the height that he's at is 8 meters. Well, whenever you see a projectiles problem, you want to use an x, y, t table. And so the x here is going to be your unknown thing that we're going to eventually find. But we do know the vx is 10 meters per second, and we know that the y, the height, is 8 meters. All right. Let's go back this way. And I actually wanted to have these equations on this slide as well, so we can all look at them together as we solve this one. This is just the equation we've been using lately, so I'm going to put those back up for us. Perfect. All right. Now, we also know in the y direction that g is 9.8 meters per second squared, so we have that known value right there. And let's go ahead and see which side we can solve for time. Well, time is always going to be solved on the side with the most amount of information. And since we're in the y direction, and because this is a horizontal projectile, because its v initial y is equal to 0, it's not going up or down when it gets thrown out the window, right? It has a v initial y of 0. We are able to use this equation, t equals square root of 2y over g. So let's try that out. T equals square root of 2 times 8 over 9.8. And we're going to go ahead and throw that in our calculator, square root of 2 times 8 divided by 9.8. Okay, that gives us 1.27, I'll round it to 1.28, the way the decimal's coming out here, seconds. Now, because it's a horizontal projectile, the time it takes to fall 8 meters is equal to the time it spends traveling horizontally. And that's why we can apply this time over this side, 1.28 seconds. Now we need to solve for x. So really, if we think about this carefully, if we look at x, all right, and look at this equation right here, when you throw something and it's a projectile, its horizontal acceleration is 0. So that whole term goes away with the acceleration. If you multiply something by 0, the whole term goes away. It's just 0, right? So we don't have to worry about that. And then you'll notice that we have x equals vi times t, right? And we've seen this one before, is delta x equals v times t. And so that's the one we're going to use. We're going to say x equals vx times t, which is going to give us 10 meters per second times 1.28 seconds. And so here, for the distance, we have 10 times 1.28 is 12.8 meters. So that's the distance that the Xbox is going to land away from the building. Now, things get a little more complicated when we go to angled projectiles, but we're going to use the same strategy. So let's take a look at an angled projectile and see how it's a little bit similar and see where it's different as well. So we have an angle of 50 degrees above the horizontal. So that's like this. That'd be 50 degrees. And the velocity here is 35 meters per second. So v equals 35 meters per second. Now, the first thing you always want to do when you see an angle for an angled projectile is to find the Vx. So we're going to get Vx and we're going to get the Vy. And as a reminder of how you do that, it's V cosine theta for Vx and V sine theta for Vy. So we plug these numbers in and we get 35 meters per second cosine of 50. And we get 35 meters per second sine of 50. All right, so let's calculate those guys and we'll drop it in there and make sure your calculator is in degree mode. And that will get us the right answer. So 35 cosine of 50. That gets us 22.5 meters per second. And Vy gets us 35 sine of 50, which is 26.8 meters per second. Boom, just like that. So you're like, well, how does that help us? It says, how far will the arrow land away? And it says, what's the maximum height the arrow will attain? So we have a lot of things to still figure out here. I'm going to move myself up here. So let's look at the x, y, t table. X, y, t. Vx equals 22.5 meters per second, and Vy equals 26.8 meters per second. G equals 9.8. That always goes on our y side, and that's always going to be the part that we kick into the problem with. Now, it asks for the maximum height the arrow will attain, and so that's up here. And because this arrow is launched from and lands at the same height, close enough, right? Because it does say that, it's asking about how high will it go. And so in order to do that, we know that the time it takes to go up is equal to the time it takes to go down. So we can use, again, this special free fall equation right here. So we're going to do that. So let's go ahead and do that. So we have the time it takes to get to the top is going to be square root of 2y over g. But we get stuck because we don't know what the height is. So there's a couple different ways to do this, but I've given you a special equation on your equation sheet. All right? And where's that one? It's this one right here. This only works for when the angled projectile lands at the same height from where it started, but it says t equals vy over g, all right, which is actually just a rearrangement of this problem. So we run into an issue there. So we say t equals, this is right under your chapter 6 part of your equations where it says time to apex, and that's going to be vy over g. All right, so let's use that one. So we have 26.8 meters per second divided by 9.8 meters per second squared. And that's going to be the time it takes to get up there to the top. Yes, of course, I'm going to keep what I just worked so hard to write. And so we go to this one here, and we got 26.8 divided by 9.8. So that's going to be 2.73 seconds. Now, that's how long it takes. T equals 2.73 seconds. That's how long it takes to get up to the top. And if the question says, how high are we when we get up there? What's the height when we're up there? Y is how high. So now we can use this one. Y equals 1/2 gt squared. It's going to be 1/2 9.8 times 2.73 squared. So that's our height. That's how high we go up there. 0.5 times 9.8 times 2.73 squared. Cool. So that is getting us 36.5 meters. So that's our answer for that first part when it says what would the maximum height be? Y is how high? Y is 36.5 meters. All right, cool. What about the second part? It says, how far will the arrow land from the launch position? Well, that's delta x. So here's a cool little trick we can do. If it takes 2.73 seconds to get to the top, it also takes 2.73 seconds to get back down, which means the time that it's in the air in the x direction is twice as much as the time it takes just to get to the top. So what we do is we take our time here, 2.73, and we double it to bring it over to this side. Keep in mind why. Because the time we initially calculated was half of the arc, but we want the whole arc, so that's why we have to double it. So 2.73 times 2 gets us 5.46 seconds. Now, x equals vx times t. All right, 22.5 times 5.46. And x, the distance, is 22.5 times 5.46. All right, so that's going to be 122.8 meters. So that's the solution for that second practice one that I wanted you to do. You'll notice that these are all old equations that we've already looked at. So it might be some new ideas, but there are no new equations. There's just new ideas and new ways to apply them. So until next time, as you complete these two problems and the page before this for the Week 18 Asynchronous 1 lesson, you will come back ready to go either with our first lab, which is launching into a cup, or the second lab, which is doing calculations for 2 angled projectiles. So until next time in the lab, I'll see you. It's Mr. Simpkins in the Simpkins Physics Corner.